Okay, so maybe you're going to hate me, but let's go over the 5 steps. And the first step is to read the question. Second step is to read it again. Third step, draw what we can. Fourth step, put what we know down. And the fifth, start going about solving it. I guess going from the known to the unknown is my way of explaining that. Okay, so let's do this then. A distress flare may be launched from a boat. That's like a firework, if you're not sure. May be launched from a boat to signal for help. A flare was launched from a stationary boat at an angle of 30 degrees to the horizontal. The flare was launched to the right from the launch position marked X. That's here. On the boat in the diagram below. Complete the diagram to show the path taken by the flare before it hit the sea. Okay, this is the first part. I'm going to read this again. So, distress flare, we get this. A flare was launched from a stationary boat at an angle of 30 degrees to the horizontal. So, that's the launch direction, and I'm going to put this in as 30 degrees to the horizontal. Okay? And that means that in the vertical direction, this angle is 60 degrees. And from the position marked X, complete the diagram to show the path taken by the flare before it hit the sea. Well, with a slightly different colour, so it will initially go at this angle, but it won't stay there very long because of something that lives in the centre of the earth called gravity. That's a little joke. And it will make a parabolic shape and it will come all the way down into the sea. And it's important that this is even, symmetrical about the highest point. So you'll get a mark for that, don't worry about it. And this is the maximum height. And I think we're going to have to do something with this in a minute. But then it's actually going to hit the sea there. Splash. I've extended the sea because I can, and that's fine. The maximum height of the flare above the launch position was 42 meters. So we're going to write that on there. Show that the flare was launched at a speed of about 60 meters per second. The maximum height was 42 meters. I've written on, show that the flare was launched at a speed of about 60 meters per second. So this launch speed, U, has got two components. Whenever we hear maximum height, we're always going to use the vertical component. And usually in projectiles, so this is when we're now known to the unknown. So what's the process of solving a projectiles? Nearly always you split it into parts, split into stages, if you like. And the stages is like part 1, which is going to go, the first part, which is everything that happens up to it reaches its maximum height. 1, so to the top, max height. And then secondly, 2, then to the end or the bottom when it falls. So in this case, it's this bit. And it won't always fall to the same height it started with. In this case, it won't, because it'll actually go into the sea, so there'll be a slight height difference there. And the time that it takes to go from this point to the middle and then this point to the end will be exactly the same. So that's the idea of this. You split it into two parts, and the time that it takes to go up, time to go up is equal to the time to go down. At least back to the same position. It won't actually get into the sea in that time. It'll take a tiny bit longer to get into the sea. Okay, so maximum height vertical component. So you split into the stages and then you split. So if you call this part A, or strategy A, and then you're going to, in doing that, the other strategy is to split into components, and the components are always vertical and horizontal. And the reason we do that is mainly because we can separate out the effect of gravity, which only works in the vertical component direction. And that means that there is no acceleration. If you ignore air resistance, there's no acceleration on the horizontal component. So that means the initial horizontal velocity will be constant. It will be the final horizontal velocity. There will be no change in horizontal velocity. So first of all, let's show that the flare was launched at a speed of about 60 meters per second. Well, you might know that this is a SUVAT question because you've probably done enough of these. And then you're going to, first of all, I think it's a good idea to write down what you know. It's only 3 marks, so I'm not going to spend ages on it. But we do know the 42 meter distance. This is just for the vertical component, maximum height. The initial velocity, we don't know that. We will be showing that it's about 60 meters per second, but we don't know what the initial velocity is yet. Now, the final velocity, we do know this is 0 meters per second because it's reached the top. The acceleration we know is 9.81 newtons per kilogram minus its acceleration is down. We don't really ever have to worry about that. Time, we don't know, and we don't need to know because we've got SUV and A, and we can use the SUVAT equation, which is V squared equals U squared plus 2AS. Rearranging these with this being equal to 0. V squared is equal to 0, so let's write it out step equals U squared plus 2AS. This rearranging, U squared is equal to minus 2AS. And U, now luckily this A is negative, which means that this negative disappears. So U squared is equal to the square root of 2AS, was equal to the square root of 2 times A, 9.81 newtons per kilogram, times the distance, which is 42 meters. And this is going to be something that we do on a calculator. And I'm actually going to do it and type it all in. So unfortunately you can't see that, but so you know what I'm doing. I'm doing this sum. I'm going 2 times 9.81 times 42. Gives me 824.04, and I'm going to take the square root of that, and we get this as equal to, so this is the U is equal to 28.7 meters per second. Now this is the vertical component. So probably if we want to relate this to this U, we would say that this is UY is equal to 28.7 meters per second. Now that's UY. UX we'll do in a minute in this direction. Now what we've got to do is we've got to relate that to the initial velocity, the launch speed. And so we can use the fact that this angle, and as a result of this, let's do this in green. This is going to be UY over here is going to be equal to U cos 60 degrees. So U cos 60 degrees equals 28.7 meters per second. And this means that U is equal to 28.7 divided by cos 60. Now we should all know that cos of 60 is 0.5, and so that gives us something like 28.7 divided by 0.5 equals something like 50. Well, it's just times by 2, isn't it? 28.7, 57.4 meters per second, which is about 60 meters per second. Therefore, U is about 60 meters per second. Nice. Second half of this. The flare was visible from a maximum distance of 8 kilometres. A rescue boat was 8.2 kilometres from the boat in distress. Determine whether the flare travelled a sufficient distance to be visible from the rescue boat. You should assume that the flare was launched in the direction of the rescue boat. Read it again. The flare was visible from a maximum distance of 8 kilometres. Okay, a rescue boat was 8.2 kilometres from the boat in distress. Determine whether the flare travelled a sufficient distance to be visible from the rescue boat. You should assume that the flare was launched in the direction of the rescue boat. Well, okay, so let's go back. Let's draw this then. So we've got this boat here, and we know that the flare was launched in this direction. So we assume that this is the distress boat, boat in distress, and this is the rescue boat. Now, obviously, it's not going to be. The rescue boat is over here somewhere. Rescue boat. And we've got, what do we know? We know that this distance is a total 8.2 kilometres. And we know that if the flare landed such that this distance here, if this distance is less than 8 kilometres, then we're good. Flare is visible. So that means that this distance here, if it's 8.2 kilometres away, I mean, I haven't drawn it to scale, but this distance here, which I'm going to say the horizontal distance, Sx, what we need is if the horizontal distance that the flare travels is greater than, well, 8.2 kilometres minus 8 kilometres, which is equal to 200 metres. So if the flare travels more than 200 metres, then it can be seen by the rescue boat. So this question is really saying, how far did the flare go, and was it more than 200 metres? So the reason we split things up like this is that we can find the time it takes to go to the top, and then the time it takes to go to the bottom is double that. And that time, the vertical time, is also, because it's the same thing, it's the flare, it might have gone up vertically and horizontally, but the vertical time is the same as the horizontal time. So what we're going to do is find T1 time to max height. That's the first thing we're going to do. So if we look at this here, T1 takes us to there, and then the same time takes us to there. So the whole time, the time of flight of the whole thing is time of flight is equal to 2T1, however long it took to get to the maximum height. Well, we know that the maximum height, distance vertically, is 42 metres. And what else do we know? Well, we know the initial velocity. We know the initial velocity y is equal to 28.7 meters per second. We know the acceleration due to gravity. We know this guy, and this is 9.81 newtons per kilogram. I could write meters per second squared, but I like newtons per kilogram. There's a gravitational field strength, which I prefer. And also it's minus. And that's probably going to be enough, because we can use the SUVAT. Let's use this one. We want time, don't we? Yeah. So let's use V equals U plus AT. And we've got V, obviously, is equal to 0. meters per second at the top. So this is 0. 0 equals 28.7 meters per second plus 9.81, well, negative, so it's going to be minus, times the time, t1, and then I'm going to put that in as minus 9.81 newtons per kilogram. And what we can do then is t1 is equal to 28.7 meters per second divided by 9.81 newtons per kilogram. So we're going to do this divided by equals 2.93 seconds. So the overall time of flight is equal to double that, equals 5.85 seconds. And we now need to find the horizontal distance. But luckily, this is very easy, because the horizontal distance we can always find from horizontal distance is equal to the horizontal velocity times the time. Now you can say ut plus half at squared. We can write that in if we want to, plus half at squared. But of course, this all disappears, seeing as there's no horizontal acceleration. And then the horizontal velocity, which we know is, it's the same 57, what did we work out it was? 57.4. So this is 57.4 meters per second. And the angle is 30 degrees. So it's cos 30 degrees. So equals 57.4 meters per second cos 30 degrees times 5.85 seconds. So we're going to times it by 30 cos times 57.4. It comes out as 291 meters, which is greater than 200 meters. So we're good. So let's go for a different color. Flare is visible. Right. State one assumption you made in a well, there's two assumptions, I think. The first is that assumption number one is that there's negligible air resistance. And the second thing is, I guess, we're assuming that it's the total distance flare travels is the important thing. Because it mightn't be the total distance, because actually what you really want is maximum height. Because obviously if it's now falling, does it matter really? It might be not really visible from a great distance. So I think what you could do is you say total distance flare travels is the important factor. Because you could say, well, maybe it only goes 145 meters to the maximum height point. And so maybe, it isn't going 200 meters. But of course, it could be seen for some of this. It's just that it's not going to be visible for all this part. So, I mean, that's a problem with the question, but they don't really expect you to say that. I guess a third thing is that the flare hitting the sea isn't a big deal. Isn't a big deal. Because actually, it's going to go a little bit further before it hits the sea. because the boat was not quite at sea level. It was like probably a couple of meters above sea level. It's not going to make a big difference, but there you go. Okay, so that's the calculation question, mechanics, and step by step how to do it and thinking about it. And you could argue that I'm going a bit slowly, but I think it's important that you know what I'm doing.